Hello everybody and welcome to my 10th video. This is on base N, JK and T flip-flops. So we're going to start with the T flip-flop. Here we can have this is the short form truth table of the T flip-flop. This is the long form truth table of the T flip-flop. Here we can see if T equals 0, Q plus, which is the value of Q after you've applied the clock, is Q. And if T equals 1, Q plus equals Q plus 1, which is modulo Q plus 1 modulo 2, which is the not function. Here the long form truth table. Here we can say if T equals 0, Q plus equals Q. If T equals 1, Q plus equals not Q. I can describe the value of Q plus by an equation. Q plus equals T and Q, or not T and Q. Now we're trying to devise a base N method, but the equation only uses a not function, which is only in the binary world, Boolean. So I have to use a different equation. So this is the definition of the exclusive OR function. So we're going to say Q plus equals T exclusive OR Q. Now the exclusive OR function is the modulo sum function, but you can apply that to any base, so modulo 3, modulo 4 for example. So we're going to use this equation to synthesize a function for base 3 ternary and base 4 quaternary. Here we have the truth table, short form truth table and long form truth table for the ternary system. Here we can see that Q plus equals T plus Q. When T equals 0, Q plus equals Q. When T equals 1, Q plus equals Q plus 1. When T equals 2, Q plus equals Q plus 2. On the long form truth table, Q plus equals, when T equals 0, Q plus equals T plus Q, which is there. When T is a 1, Q plus equals T plus 1. When T equals a 2, Q plus equals Q plus 2. On the quaternary system, 4 logic states, here we have the short form table and the long form table. And we can see again Q plus equals Q when T equals 0, Q plus 1 when T equals 1, Q plus 2 when T equals 2, and Q plus 3 when T equals 3. Here on the long form truth table, when T equals 0, Q plus equals Q. When T equals 1, Q plus equals Q plus 1. When T equals 2, Q plus equals T plus 2. And when T equals 3, Q plus equals Q plus 3. Okay, so that's the general strategy for generating a T flip-flop in any base N. So now we're going to move on to the JK flip-flop. This is the binary JK flip-flop, and we can see the short form truth table and long form truth table here. Here when J and K equals 0, Q plus, which is the value of Q after the clock is applied, is Q. J equals 0 and K equals 1 equals a 0. J equals 1 and K equals 0 is a 1. J equals 1 and K equals 1 equals Q plus 1 modulo 2, which is not Q. And here we can see on the long form truth table, when J equals 0, Q plus equals Q. When J is 0 and K is 1, it's 0. And when J is 1 and K is 0, it's a 1. And when J is 1, K is 1, it's not Q. There. So we can derive an equation for Q plus. Q plus equals J and not Q, or not K and Q. Again, for the same reasons, we're trying to develop a base N system, and the not function only exists in the binary world, so we can't use this equation. So we're going to have to use a modulo sum and product function algebra to derive the equation for Q plus. Here we have the binary modulo sum and product function table. This is how you derive the function q plus here. This is q plus equals 1. You've listed j, q, k and j when q equals 1 here in the truth table I just shown you. Basically, coefficient of j to the 1 or k to the 1 or q to the 1 equals 1, or j to the 0 or k to the 0 or q to the 0 equals not j, not k and not q respectively. Basically what I'm doing is I'm taking each line, evaluating each line of the truth table here and summing the digits here. If you don't understand what I'm doing here, please watch my video on a base and modulo sum and product algebra, and that'll explain it in more detail. Basically, I'm taking the coefficients here and displaying them here. So here, adding up the ones, 4 ones equals 0 mod 2, 3 ones equals 1, 1 equals 1, 1 equals 1, 1 equals 1, and 2 there, 0 and 0 there. So I'm taking the non-zero terms, so j and q here, k and q there, q there, and j there. So we have an equation for q plus. So q plus equals j and q, exclusive of k and q, exclusive of q, exclusive of j. So I've factorised out the q, so q plus equals j exclusive of k, exclusive of 1, and q, exclusive of j. So I'm going to use that expression to derive the function for a base n jk flip-flop. So here I have the jk function table again. I've written it out slightly differently. Here's j and k inputs. This is q plus when q equals 0. This is q plus when q equals 1. Now I've taken the value of q to the 1 here, which is j plus k plus 1 modulo 2, and q to the 0, which is j. I've just rewritten that there. And the function q is q, 1q plus 0, 0, 0q plus 0, 1, 0q plus 1, q plus 1, 1q plus 1. So this is how you generate the function. You take the coefficients of q to the 0 and write the function there. Then from this function you work out the values of q plus the various values of q there. So the excitation table here, I'm going to go from a q0 to a q plus of 0. So q is 0 and q plus is 0. J equals 0 there, but k can equal any value. So here, q is q from a 0 to a 0 to q plus. J equals 0 and k can assume any value x, 0, 1. Same one with 1. From 0 to 1, 0 to 1, j is 1, k can assume any value 0, 1, so it's an x, so that's 1x for 0, 1. 1 to 0, 1 to 0 here, so k is a 1 and j can assume any value 0, 1, so there. And q to q plus is a 1 to a 1, so 1 to a 1, so k equals 0 and j equals x there, 1 to 1. K equals 0, j can assume any value 0, 1, so an x. So here we have the ternary function table. It's a similar table to the jk function table in the binary case. Here we have the value of q plus when q equals 0, q plus when q equals 1, q plus 1, q equals 2. J and k are listed there. They can assume a value of 0, 1 or 2 in the ternary case. The coefficient of q, j plus k plus 1 modulo 3, and the value of j, q to the 0, which is j. And basically use this to write the function there, q, 2q there, 0 there, 2q plus 1 there, 1 there, q plus 1, 2, q plus 2, and 2q plus 2. I'm just following the coefficients of these and writing them in the function. So from the function you can work out the value of q plus from the value of q. So a q function there is q, so a 0 there, 1 there, and a 2 there, no change. For 0 here, when j is 0 and k equals 2, q plus equals 0 no matter what the value of q. Same here for 1s, same here for 2s. You have q plus 1 here and q plus 2 here. Q plus 1 is a successor function, which is the 1, 2 in response to 0, 1, 2, and q plus 2 is the predecessor function, which gives a 2, 0, 1 in response to 0, 1, 2. I must say that the only useful functions really are the 0, 1s and 2s, and q plus 1 and q plus 2, because if you take 2q plus 1 and q equals a 2, q plus equals a 2, so it locks up. So some of these lines for settings for j and k aren't really usable, but it's still a useful circuit to have. Right, I'm going to move on to the JK excitation table. I'm going to explain how a 0 to a 0 works for j and k. Basically, when q is a 0, then q plus is a 0, j is a 0, and k can assume any value, 0, 1 and 2. So, when q is a 0 and q plus is a 0, j is a 0, and k can assume any value, 0, 1 or 2. So I've marked that with an X. One trait of these truth tables is that the first n rows of the truth table, k is an X, don't care state, and j is the values of n in ascending order, 0, 1 and 2, 3, 4, etc. And the last n rows, j is an X and k is the values of the base in descending order, 2, 1, 0 or 3, 2, 1, etc. For the middle rows, for q1, q equals 1 to q plus equals 0, value of x can assume any value, 0, 1 or 2, but the value of k must equal j plus 2. So whichever value you've chosen for x, that's that value plus 2. For j equals, from q equals 1 to q plus equals 1, j can assume any value, 0, 1 and 2, but k must equal j. And for transition from a 1 to a 2, value of j can equal any value, 0, 1 or 2, but k must equal j plus 1. You could swap these around and have the x's there and the functions of k there. So that's basically the ternary JK excitation table. Next we're looking at the quaternary JK function table. Here we have the values of q plus, when q equals 0, q equals 1, q equals 2, q equals 3. Written the coefficients here of q plus 1, when q equals 1, j plus k plus 1 modulo 4 is the coefficient of q, so that's there. Coefficient of q to the 0 is j, so that's there. J and k here, assuming the values of 0, 1, 2 or 3 in the quaternary case. And I've written the functions here as just straight copied from q to the 1 to q to the 0 here, coefficients here. So 1q times 0 there, 2q there, 3q there, 0 there, 2q plus 1 there, 3q plus 1 there, 1 there, q plus 1 there, 3q plus 2 there, 2 there, q plus 2 there, 2q plus 2 there, 3 there, q plus 3 there, 2q plus 3 there, 3q plus 3 there. So again, first line of the truth table, when j equals 0 and k equals 0, function equals q, so a 0, a 1, a 2 and a 3 there. Again, some constants here. When j equals 0 and k equals 3, the function equals 0, so q plus equals 0 regardless of the value of q. 1s, same for the 1s, and a 2 there, and a 3 there. We have q plus 1, q plus 2 and q plus 3 there. Q plus 1 is a successor function modulo 4, and q plus 3 is a predecessor function modulo 4. So again, some of these functions are unusable, so if you take the value of 2q plus 1, if q is a 3, q plus is a 3, so again it locks up. So some of these functions are unusable, but the values of 0, 1, 2 and 3, the constants, the values of q plus 1, q plus 2, q plus 3 are usable. So the basic idea for say a quaternary system, you would get the values of q to the 1, q to the 0, work out the values of the function, and from there work out the values of q plus. So we're going to move on to the Quaternary JK excitation table. I'm going to show you how to do the last line of this truth table. So I'll just put this one back. So q is a 3 and q plus is a 3. We have a 0, 0 there, a 0, 1 there, a 0, 2 there, and a 0, 3 there. So j can assume any value 0, 1 and 2, but k must equal a 0. Right. So here we have a 3 to a 3. J can assume any value 0, 1, 2 or 3, and k must equal 0. So here we have the first n rows of the truth table, k equals x, and j is the numbers in ascending order. The last n rows, the last 4 rows of the truth table, j equals x, and k is the numbers of the base in descending order. For the middle 2 rows, say for a q equals 1 to a 0, j equals an x, which is any value 0, 1, 2 or 3, but the value of k must equal 2j plus 3. For a 1 to a 1, value of x, j can equal x. Whatever value you choose, k must equal 2j. For these rows, the last bottom middle 4 rows, so if you had 2k plus q equals 2 to a 1, k can equal an x, but the value of j must equal 2k plus 1. For a value of 2 to a 3, k can equal x, but the value of j must equal 2k plus 3. Modulo 4. All calculations are done modulo 4 for the quaternary system. Right. I think that's about it. That concludes the presentation. Thanks for watching. Bye.